Okay, thanks a lot. So I'm going to present overview a number of results that has been achieved together with my colleague at the math department, Gennaro Ricchio, Andrea Codegoni, Marco Veneroni, Leonora Vercesi, Giuseppe Toscani, and Federico Bassetti, who moved to Polytechnic of Milano, and with Pierre-Yves Boucher, and who is at Montreal now, Luis Martin Rousseau, who will speak later on this seminar. So the plan of the talk is to give a brief introduction to optimal transport with a combinatorial optimization perspective, and I will anticipate the application of the network simplex in machine learning, and then I will move to a brief description, technical description on a possible parallel implementation of the network simplex that try to exploit a GPU. And finally, I will present just one slide of computational results. So optimal transport is like, go back, it's really an old-fashioned talk. It's an old problem. It's like 250 old problems introduced by Monge, where in his original paper, he was talking about the distribution of molecules and how to move a distribution of molecules from a given origin shape to a target shape. Nowadays, when we talk about optimal transport, we talk about probability distribution, but the original problem of Monge can be like formulated in combinatorial optimization. Sorry, let me hide the zoom panel. Okay, it can be formulated like an assignment problem, which can be solved in strongly polynomial time with flow algorithms. That is in bipartite graphs that are usually solved that are usually used to formulate optimal transport problem, can be solved in an n-cube problem. So it's polynomial, but is quite high power in the complexity. From Monge, there is a really important contribution to optimal transport by Kantorovich, who is not only the inventor of duality theory of linear programming, but is also the researchers who introduced the transport matrix that nowadays is known also as a Wasserstein matrix or Kantorovich-Wasserstein matrix. And the original works of Kantorovich was motivated by application on a resource optimization problem and was written in Russian. In combinatorial optimization terms, the Kantorovich problem is different from the Monge because we move from an assignment problem to a transportation problem. And the complexity, the strongly polynomial complexity, raised to n-cube log n on bipartite graph. So this is somehow an important point. In modern terms, optimal transport is not related to molecule, but more, as I said before, to probability distribution. And the problem can be formulated on general measure as follows. Given two distribution mu and nu, and given a cost function that lies on the space where the two probability measures are defined, we can define the Kantorovich-Rubinstein functional as the infimum over the joint probability measure of the defined over the two probability measures given an input that minimize the cost overall cost over all possible joint probability distribution. Instead of staying with the continuous formulation, I like to move to discrete probability measure that is defined in terms of Dirac delta measure. That is, delta Dirac is defined to be 1 for a given, whenever we have a subset of the space, the probability set that belongs to. So we have a support point that is equal 1 to 0. And we can define discrete probability measure in terms of a weight and a support point. So with points and weight, points in a space where the probability distribution is defined and weight associated to each support point. The basic example is like grayscale images can be interpreted as a discrete measure where we have a pixel position, give the position xi, where we have a delta, and we have the intensity that is the weight of that position. Computationally, we can distinguish among 3 different cases of optimal transport. And just mention all the 3 just to try to focus on one of the 3 for the rest of the talk. We can have that both the probability measure lies in continuous space, or we can have one probability distribution that is continuous and the second in discrete, or we can have that both probability measure are discrete. And when both are discrete, solving the Kantorovich-Rubinstein functional defined on discrete space, it boils down to solve a linear program, which is a strongly structured linear program, because we have a formulation that can be given in terms of a bipartite graph. The interest of this basic linear program is that the contribution due mainly to Kantorovich, also is now the matrix called Wasserstein matrix, but should be the Kantorovich-Wasserstein matrix, is that whenever in this linear program, we have a cost function for moving one unit of mass from one position of the first space to one position of the second space. I mean, whenever this cost function is a distance, so is a matrix in mathematical term, in axiomatic distance, so it's really, I mean, reflexive, staying the same point is equal to 0, and we have triangular inequality. So whenever the C cost function is a distance, we can define the Kantorovich-Wasserstein metric of order P as the linear program where in the cost function we have the D power of a distance, and then we take of the optimal value, we take the minimum between 1 over P and 1. So the idea is that with the Wasserstein matrix, we have a way to compare probability distribution to measure a distance between probability measure, not a distance between a pair of points in a space, but a distance between a cloud of points, a distance between a pair of probability distribution. And this distance, the value of the distance, is given by the optimal solution of a linear programming problem. So in machine learning, optimal transport is really, nowadays, it's really linked to entropic regularized version of the problem, where in the cost function, we had regularization terms that depend on a parameter epsilon. And when epsilon is equal to 0, we recover the optimal transport. But the entropy regularized cost has a really important advantage from a functional analysis perspective. But if epsilon is different from 0, we really don't have a true matrix. And the reason why this really use the entropic regularized version is because of the Sinkhorn algorithm that can solve really efficiently the transport problem, in the sense that it can estimate the optimal value in a time that is like n squared divided by the square of the accuracy, I mean, of the regularized parameter. But here we are not really getting an optimal transport plan. And there are applications where we really want to use the optimal transport plan, and we'll try to convince you with an application a few slides later. Another really advantage of the Sinkhorn algorithm is that it can really be implemented easily and very efficiently on parallel hardware. It can really exploit your GPU. But in practice, we have to handle with care because it has stability numerical issues. If you are only interested in getting the optimal value of the distance, we recently proposed an alternative that is based on the Fourier matrix. So we go now from Kantorovich to Fourier. And in a recent work, we proved that the Fourier matrix is mathematically equivalent to the Wasserstein matrix, and it can be computed very efficiently with fast Fourier transform. And moreover, the matrix is fully differentiable and can be interested for other application. But I will not talk about this in this presentation, because here the focus is more on a combinatorial optimization version on optimal transport that we want to solve with the network simplex, because we experimented with a number of cases, and it is the fastest from the flow algorithm. And we really want a true matrix in mathematical sense to be used in machine learning application. We might need the optimal transport plan. So we cannot only stay happy with the approximation of the optimal Wasserstein distance. And there is, yes, it's more a personal flavor. We're really trying to make an effort to see if we can exploit GPU for pure combinatorial optimization algorithms. That is quite hard. So let me check time. Okay. So now I anticipated, given the other talk on this seminar, the application of machine learning, since the workshop is deep learning and combinatorial optimization. And another recent work that I've done with my colleague here in the department is to try to introduce what we call the gene mover distance, like to mimic the name of Earth mover distance or world mover distance. There are other applications where the optimal transport distance have proved to be very successful. In this case, we are defining a distance to compare single cell. And the application is for analyzing high quantity of data that come from single cell RNA sequences. And the idea is that each cell can be characterized by a gene expression profile, and we can somehow interpret a gene expression profile like two discrete probability measure mu and nu. And the issue here is that if we want to have an optimal transport distance between gene expression profile, we need to define what are the weights. But this is easy because the weight of the two distribution can be the expression profile, that is an integer that somehow is count a given quantity of the expression of the gene in the RNA sequences analysis. And then we need to define a distance between two genes. To define a distance between two genes, we used embedding gene2vec that has been published a couple of years ago, that using deep learning technique, what they were doing is to associate to each gene, and the human cell can have up to 30,000 different genes. So to each gene is associated a vector of R200. And the reason is 200 because in the paper they tried different value of the space, and then the 200 were given the better result. And so we can associate to each gene a vector, and then to define the cost function that appear in the optimal transport problem. So the cost here, that is the crucial point, that has to be a distance, has to be a matrix. We define the as a distance, the L2 norm between the vector associated to a pair of genes. So what we get here is a bipartite graph where we have a node for each gene, and we have one partition for one cell and another partition for another cell, and we define the cost as the distance between the gene corresponding to each node. We can solve the optimal transport problem, we can get a measure of distance between two cells. If we have a bunch of cells that we want to classify, we can compute the full distance matrix between the pair of cells, and then we can run like k-nearest neighbor to classify the cell. Alternatively, the optimal transport, we can define a different ground distance. We can use a different cost in the linear program. As for instance, we can use the Pearson distance. I mean, it's based on the Pearson correlation coefficient. If we take the square root, we really get a distance. So even the optimal transport is a distance. And then as the same way, we can compute a full distance matrix between a pair of bunch of cells, and then we can try to classify the cell accordingly. And in this application is in a case where we compute pairwise distance using the network simplex, and we need the optimal value, and we need the metric properties of optimal transport. And the result that we get on simple classification problem, for instance, to classify binary classification for acute myeloid leukemia cells, and we want to classify cell as normal or malignant, is that using the two variants of the gene mover distance, we can have pretty good accuracy despite the simplicity of the classification algorithm that we use. But here the objective was more to measure the strengths of the optimal transport measure, or we can achieve a multi-class classification on 14 different classes. And here we have 4 patients, and this is a tumor for a human pancreas. And we want to try to classify each cell as belonging to one of the 14 classes. And here we can see that the gene mover distance, that are the box plots on the most right part, really again perform really good accuracy, like more than 90%. And here we are comparing the optimal transport distance that we call gene mover distance with basic distance. I mean, it's not basic, but the two distances that are most used in the genome literature, that are the Euclidean distance between gene expression profile and the Pearson correlation, which is no distance between the gene expression profile. So this is the first example where we use a network simplex, and we use as a motivation to make a major effort to implement a parallel version of the network simplex. The second motivation is for completely different context, where we are interested in computing barycenter of probability measure. Here we start with the idea of trying to compute the barycenter of two measures I just give you the time to read the definition. I will try to stick on the example with the images. So suppose we have a discrete measure that is the digit 9 on the left, and we have another measure that is another digit 9 on the right. What we can do here, we can solve an optimal transport problem between the two discrete probability measures. We get the optimal transport plan. So we know how much of mass from one pixel move to the other pixel. And we do by using the network simplex. And then we can exploit what is the interpolation properties of Wasserstein distance, of Wasserstein matrix. Let's say that once that we have the optimal plan, we can interpolate between the two measures. For instance, we can take a value for a parameter here, like t is equal to 0.3. And for the t, we fix the weight that appear in the barycenter. And we can somehow interpolate like a time t is equal 0.3, where all the mass were moving from one distribution to the other. So we can do for any value of t, we can really get a true smooth interpolation between the two measures. And this is a nice property where we need to solve the transport problem exactly, and where we need the optimal transport plan, and not only the Wasserstein distance, the value of the distance between the two measures. Once we get these nice interpolation properties, we can play with, and we did with Ruiz-Martin-Rousseau and with Pierre-Boucher last year, CPOR 2020, we can define Primal heuristics that iteratively try to pair of discrete measure. They interpolate between the two measures, they get a new measure, and we keep on making pair iteration. I will not go into the detail of the heuristics, but the key is there is that what is used for. Suppose we have a bunch of probability measure, and we want to find the most representative measure of all the digits. So we really want to find the barycenter of all the discrete measure. If we apply our heuristic, like over 50 images, we can really get the Wasserstein Barycenter by computing a sequences of optimal transport plan, then making the interpolation that is possible thanks to the property of the Wasserstein matrix of order 2, and then we can get to barycenter, for example, for digit 9. And this problem can again be formulated as a linear program and can be solved to optimality using Barren algorithm. And it take like on a 50 digit, it take like 800 seconds, the gap is 0. And if we apply one of the 4 variants of our algorithm, we can get a gap that is like consistently smaller than 1% and is running 7 seconds, while the computational Wasserstein Barycenter, that is the third row up, so combo, which is based on the Sinkhorn algorithm, on a specialized Sinkhorn algorithm, is somehow slower, and you get a gap to optimality that is in average greater than 1%. So up to now, I hope that I convinced you that the network simplex that permit to solve the optimal transport problem to optimality and it permit to get an optimal plan that is feasible is an important component and can play an important role in machine learning pipelines. So now I go more on the technical part of this talk, where I try to give you some hints on how we can implement a parallel network simplex algorithm. Okay, if you don't know what is the network simplex, it's really something that is very similar to the linear programming simplex algorithm, and I give for granted you have some basic knowledge of the simplex algorithm. And the idea is that in the simplex algorithm, we iterate among 5 steps that we generate an initial basic feasible solution. We choose an entry variable, we choose the leaving variable, we pivot out variables and pivot in the entry variable, and we adapt the basic solution, we build the dual variables until we have a negative reduced cost solution. The network simplex is much the same, but exploit the fact that on flow graph, the basic feasible solution can be represented as a spanning tree over the node of the graph. So we really have a combinatorial structure, and all the operation of the network simplex can be performed if we have integer data just by doing addition and multiplication. So it's really a pure combinatorial algorithm. And to implement in parallel, there are 2 or 3 steps that can be parallelized. For sure, if we have bipartite dense graph, we can price variable in parallel. And here, where we make the major effort to exploit the GPU, or we can perform in parallel the search for the living variables, because we have a cycle and we can visit the cycle in 2 directions with 2 parallel threads. And something that I'm trying to work recently is to try to parallelize also the update of the dual variables, which can be done not on GPU, I don't think so, but at least on CPU. But this requires a change on the data structure that you use to represent the basis tree. Nowadays, most of the implementation use what is called extended augmented thread index data structure. And the point is that in the extended ATI data structure, the basic tree is linearized. So the update of dual variables take an order, order n, so it's bigger order n, is linear in the number of nodes of the graph, and this can be quite high. While if we use the extended augmented predecessor index data structure that somehow has been rediscovered in the late 90s, we could also perform somehow dual variables update in parallel. Okay, but let's try to focus on choosing the entering arc in parallel. I want to just give you the main idea of the trick for exploiting the GPU. So if we rewrite the optimal transport problem, just here I change the equality constraints to greater or equal, lesser or equal in such a way that the dual multiplier of constraints 6 and 7 are restricted in sign. And so we write the dual problem, we get what are called the dual potential Kantorovich, U and V. What we can do is, like for using a column generation perspective or a row generation perspective, it depends on you like to see this problem, we can define a restricted master problem that is on our graph, we select a subset of variables. We do not take all of the variables. We can define this so-called restricted master problem. We solve the optimality, we get the dual value. At this point, we have to solve what is called the pricing subproblem. That is, we have to find for the minimum reduced cost variables, and as long as the minimum reduced cost variable is negative, we can add new variables and iterate. So this is pricing operation. Once we are given the cost and the dual multiplier is a very easy step that we want to do on a GPU. How? Well, the main component here is to exploit what is called the parallel mean reduction paradigm. Because on a GPU, what we have is that we can have up to 1024 concurrent threads, at least in principle, and each thread can perform, almost at the same time. It's not exactly the same time, but let's think like it was at the same time, the same operation. So here, for instance, if we have 8 variables to price, we can have like pricing the 8 variables once at the same time. So we compute the negative reduced cost, and this is the first step. And then we need to find the minimum over the 8. But if we use the parallel reduction techniques, we can at the same time compare the first variables with the 5th, the second with the 6th, and so on. And so we can compare 8 variables at the same time, and this reduces the number of pricing variables to 4. Then we can iterate to 2 and to 1. If you think that we can do this for a vector of 1024 variables, we can make a parallel mean reduction of 1000 variables, like in 10 steps. That is quite important. However, the main issue is that we need to transfer dual price from the chip, from the main memory to the GPU, and we need to get the price variable from the GPU back to the CPU. And this is done to a speed very slow, that is 8 gigabytes per second. So the main idea here is that, I have 3 minutes left. So the main idea here for the parallel network simplex is to exploit the parallelism together with what is called a sifting technique that was introduced by Bixby and others in 92. That is, we work with a strict master problem that is defined on a subset of variables. We copy the dual variable to the GPU, we make the massively parallel pricing, we get back the solution. So we get new variables to be added to the restricted master problem. We purge variables, and this is a very important step, and then re-optimize. And so we need a network simplex that also supports for one start. And we do this iteratively until we get an optimal solution. And the main idea is that why we do this kind of steps where we do not use the GPU really inside the network simplex, because there will be really a waste of time in keeping copying data from the main memory to the GPU and vice versa. We do like Sifting, that we solve a two-level master problem and a restricted master problem, pricing problem, just to limit the data transfer from the GPU to the main memory. So if we do this implementation, I have very recent results, and I will skip the technical details that are quite standard, and we use a standard benchmark of grayscale images here. What we have is this last slide of the results. So what I'm doing here. So I'm comparing the computational of optimal transport on a complete bipartite graph using the CPU parallel simplex algorithm, where parallelism means that we just make the dual update, the few operation on CPU parallel thread, with a column generation plus sifting implementation, with a GPU column generation plus sifting. For the sake of completeness, we report also a comparison with a stabilized Sinkhorn algorithm that run in parallel on 10 threads on the same machine. And here we can see that overall, the GPU parallel network simplex is very fast, and the results are average over 19 instances. And we can get a speed up like around 4 on the smallest instances, about 3.6 on the medium instances. And on the larger instances, overall, we get a speed up of order 2. However, if we look at the speed up of the pricing problem, that is where we really are running the code in parallel, the speed up is always like a speed up of 6. And what is also interesting is that on small medium instances, with this implementation of the network simplex, we are also able to, run run faster than a GPU parallelized version of the Sinkhorn algorithm. The Sinkhorn algorithm is scaled better because it's fully parallel, and then GPU is really faster, but it's not exactly an exact solver, so the comparison has always been done with care. So to conclude, if you like, the takeaway message of this talk is that the old-fashioned network simplex can still play an important role in modern machine learning application. And try to convince you with the G-mover distance and with the computation of Wasserstein Barycenters. The column generation plus sifting, which is also an old technique that is crucial to solve very large distances, and to exploit a GPU on combinatorial optimization algorithm can be done. But we really have to try to take care of the data transfer bottleneck from the GPU and the main memory. And to conclude, I like to also thank the sponsor that is sponsoring a small project for the CPU parallel implementation of the simplex algorithm. And we have a pre-release of this code available on GitHub as a C++ code with Python wrapper, and we submitted an RF wrapper to CRAN, and we are waiting for acceptance. So with this, I conclude my talk, and I'm happy to answer your question right now or later on the breakout room. Thanks a lot.